Give you one last chance. Anybody got a question on any past homeworks or anything before I get rolling? Feel free to chat them if you'd like. All right. Well, what I'm going to do is I first want to remind you guys that being my online class, y'all do have a online test, or excuse me, a face-to-face test due this week. But I did give you a little extension in that you are allowed any on Monday to get it done if you haven't gotten it done already by Friday, Saturday, or Sunday. I don't think any testing centers are open on Sunday, but I do think one of the campuses or all of the campuses, not really sure. I do think a campus or some campuses might actually have a Saturday time that you can get your test proctored. I'm almost 100% sure nobody has a Sunday, so you need to get it done Friday or Saturday, and then if you miss that, you have no choice but to get it done on Monday. Most of those testing centers need reservation basically. So make sure you call and set that up well in advance. You only have a few days. I'm not going to take any excuses. I've given you more than enough time. If Monday comes down to it and you don't have a proctor or a reservation to get a test proctored, you're going to get a zero on the test. So make sure y'all get that done. Another thing that's happened is we had an online test, test two, that was due at the beginning of this week, and for some reason I still had students that missed the first one and the second one. Uh, so I don't know. You might be dropped. You need to contact me if you realize you dropped it, or if you realize you missed the test. In hopes that maybe we can work something out where you can take it. But I'm at bare minimum going to have to take some points off because you missed the deadline, even though I gave you a second deadline as well. So make sure you don't do that. We are essentially finished with chapter five, but I told you I had a little bit of problem when I was just making up on the fly that basically a falling problem with air resistance that was proportional to the velocity. Somehow I got something in there where I ended up thinking, at least according to the math that I had done, that g could be multiplied by the e function, e to the whatever, and or actually not even g being multiplied by it, but g could have that quantity e to the something other subtracted from it, and that's just not right dimensionally. So I decided I'm going to work a problem more or less like the last problem at the end of chapter five to start today, and then we're going to go into chapter six. So that's where I'm going to begin now. Those of you, well, I shouldn't. I was going to say those of you that are here. I don't know why I would even say that, but anyways, since you're here, go ahead and chat me your first and last name. That'll count as your role, so you can go ahead and chat your first and last name. Uh, Other than that, I'm going to go ahead and share my computer screen with you so that you can see what I'm doing, and we'll start with our first example, which is more or less the last example from chapter five. So. If you don't understand something, make sure you ask me as we're going. You don't have to, chat. In fact, you can just speak up. It's fine. I understand some of you might not have the ability to speak. Maybe I don't have speakers and stuff like that, and that's fine. So I'll try to keep an eye on the chat, but I do miss it a lot. So uh, be careful. And if anybody else notices someone is trying to get my attention, feel free to let me know by speaking up. But you are perfectly welcome to interrupt me to ask questions. If it gets too onerous, there's too much of a pain, or people are too distracted, then we'll address it then. But right now, you shouldn't be any problem with it. So this is the first example I have for you guys. It says determine the velocity as a function of time for an object, that should be an object, of mass m falling from rest vertically with an air drag force proportional to v. Okay, so that's a classic conservation or a classic air drag type problem. The two forces that we normally encounter in terms of air drag is force is proportional to the velocity, or force is proportional to the velocity squared. I find that the velocity squared one is a little more often adapted to high speed things that might be going through air or through things with really high density. So I would expect, for instance, the drag on a literal submarine might be some constant times the velocity of the submarine squared, whereas the let's say the drag on a ball falling from the top of the Empire State Building, for instance, I would expect that to have a velocity that might towards the end, or an air drag that might towards the end when it started going really fast, might become more like b some constant times v squared. But a good fraction of it you can cover as a constant times v. So we're going to work with that. I'm going to choose downward as the positive direction and go from there. So here's our solution. So what we're using is Newton's second law, which says the summation of the forces. We're going to be dealing with just one dimensional, so I'm just going to write the non-vectorial version, or at least it's the vectorial version, but it's just one component of it. So the summation of forces in the y direction is equal to mass times acceleration in the y direction. I'm going to use that the force of air drag. So the force, or the drag force, is equal to negative B times V. And instead of A, we're going to use A is equal to dV dt. And specifically, since we're talking about A in the y direction, we're really saying dV sub y over dt. So if we actually imagine the object falling like this would be it with a mass m. The forces acting on it, of course, are, again, I'm treating downward as the positive direction. So this is the force m times g. And as I said, this is the positive y-axis pointing downward. And this would be the x-axis. And this up here would be the uh, negative y-axis pointing up. Now, the air drag, when you first drop the ball, because the ball is falling from rest, that means it started with initial velocity of 0. So the velocity will be very small. Excuse me, initially. So the drag force should be very small initially. So don't be misled by this vector being so short. This is F drag is equal to negative B times V. And again, since that's the only V we're dealing with, there's no need for me to subscript it Y or anything like that. So now what I'm going to do is add up all the forces acting in the Y direction. Those are mg plus negative bv is equal to m. And in this case, the acceleration is not a constant, so we can't just use a. We actually have to use the derivative dv dt. You could also use the derivative d2x over dt squared, but the way we're solving it's a little better because we can go ahead and solve for velocity and we don't necessarily have to know the excuse me, don't necessarily have to know the x position, or the in this case the y position, as a function of time. So v is really all we need. Now that I have that, I am going to first off divide through by mg. That was the way I didn't do it last time, and I'm thinking that'll keep me from running into the error that I ran into last time. So I divided both sides by mg. That's going to become 1 minus bv over mg is equal to, actually, I really wrote that poorly. I forgot that I divided and didn't record it there. So it should be 1 minus b times v over m times g, and that's equal to 1 over g times dv dt. So with that in mind, I can see that basically the left-hand side is only a function of v. So if I could get that over on the right with the dv, I could do an integral. So what I'm going to do is I'm going to multiply both sides by g times dt. And of course, like I said, whatever you do to one side, you got to do to the other. So I'm multiplying by g dt on both sides. That'll be one step. I'll take the other one in a second step. When I do that, I'm going to get 1 minus BV over mg, all of that in parentheses, times g dt is equal to, in this case, I just now have a dv. Now I'm going to divide both sides by 1 minus BV over mg. And of course, whatever I do to one side, I got to do to the other. So it's 1 minus BV over mg. Now, what I can see is I have g dt is equal to dv over 1 minus bv over mg. So that's our differential equation. What I'm going to do is I'm going to integrate both sides. So I'm going to integrate from t equals 0 to sometime t later. And I'm going to integrate this side again. This one, however, I am integrating dv, so I'm integrating with respect to v. So it's v at t equals 0, which we said was falling from rest. So that's at v equals 0. And then the top will be technically v of t, but I'm probably not going to write v of t. I'm just going to keep it as v when I'm writing it. Now, in order to do the integral on the left, that's easy peasy. The left-hand integral is clearly just gt, and then of course you'd evaluate that at t equals 0 and t, which is obviously just giving you gt. But the other side, what I'm going to do is I'm going to say let w equal 1 minus b v over mg, so that dw is equal to negative b over mg dv. So if I multiply both sides by negative b over mg, then I can get the negative b over mg in front of the dv, and things will be nice. So what I'm going to do now is I'm going to multiply this side by negative b over mg, and I'm going to take my integral on the other side, and it's now going to become negative b over mg times dv in the numerator, and the bottom, which is 1 minus bv over mg, which is literally the w. So that's just going to become w, and we can see that this quantity in the numerator is the dw we wanted. Okay, but again, remember our limits of integration were from v equals 0 to v of t. So now I can write the left-hand side, evaluating that gt at t just gives you gt, and then you do minus g times 0, which gives you 0. So you now have negative bg over mg t. You can see the g's are going to cancel out. On the right-hand side, you're going to get the natural log of w, and of course w is 1 minus bv over mg, like that, but I still have to evaluate it at v equals 0 and v of t. Now, if I carry on, what I want to do next is I'm going to simplify a little bit and make that just negative b over mt, and that's going to be equal to the natural log of, now in this case we had to do 1 minus bv over mg, so that'd be the natural log 1 minus bv over mg. That's the v of t term. Now the other term is v equals 0, so it'd be minus the ln of 1. And of course, the ln of 1 has to be equal to 0. Uh, anyways,
I had a really quick question and I might be
yeah, no
confusing
problem.
myself.
Go for it.
when you let W equal 1 minus BV over mg, and
Hmm.
the derivative of W is equal to negative B over mg, wouldn't you
Times
need to
dv.
solve that for dV so then you could substitute that? So like
That's the
divide.
Yeah, you're thinking right, but that was, and I should say that's probably the first way you do it when you first start doing the integrals. But after a little time, what you notice is because you have the dv up there, you can just go ahead and multiply both sides by negative b over mg. That's already multiplied by dv, and once you have that, you have dw. So sometimes you might want to do it beforehand, sometimes you might do it afterwards, but we took care
Okay,
of it
so
either
you
way.
multiply both sides by negative B over mg2.
Exactly.
Okay, okay.
Okay. So, yeah, and that's a good question. You were paying attention to what would normally goes on, so that's a good thing. Uh, Now what we're going to do is, since that ln of 1 is 0, we're going to raise e to the left-hand side power and set that equal to the e raised to the right-hand side power. So when I do that, basically what I'm doing is putting an e down here and putting an e down here, and the left hand side is not going to change, but the right hand side turns out the when you raise e to the ln of some argument power, then it just becomes the argument. So in this case, I'm going to get e to the negative b over mt is equal to 1 minus b v over mg. Don't know why I kept writing in blue there, but anyways, I'll go back to my purple that I'm writing the solution with. Now what I'm going to do is try to get the v by itself on one side. So I'm going to basically add bv over mg to both sides and subtract e to the negative b over mt from both sides. So that's going to give me bv over mg is equal to 1 minus e to the negative b over m times t. Now I'm going to multiply through by, well, let me go ahead and show you. I'm going to multiply through by mg over b and mg over b. And as long as the mg over b doesn't turn out to be 0, all this is fair games. That's just an ongoing thing in mathematics. Whenever I say whatever you do to one side, as long as you do to the other, it's okay. It is okay, except you're not technically allowed to multiply through by 0 or to divide through by 0. And it's not always obvious that you're multiplying through by 0 or that you're dividing through by 0, because when you do it, it might be in the form of like a variable that you only they think initially, well, it's not 0, so it should be okay, but there might be times where it is 0. The good news is, in most physical problems that are related to real life things, uh, they usually have some innate ability to protect us from accidentally dividing by 0. And it's not really so much that it's magical powers or anything. It just happens to turn out that in order for this law of nature to work out to be a law of nature, it can't have weird things like division by 0. So now that I have this, you can see that I finally get an expression for v, which now I'll finally write it as v of t, because when I multiply bv over mg by mg over b, I'm just left with v of t. The other side, however, I'm going to get m times g over b times 1 minus e to the negative b over m times t. And this is the expression that we were looking for when we were asked to find the velocity as a function of time. Anybody have any questions about that? Okay, so now you can see the only thing I'm adding or subtracting e from, for instance, is just a numerical constant 1 instead of g. Whereas last time when I did that calculation, I had g minus e. There's no way numerically that that should work out because the units don't match. E is more or less, it has to be a denominate number unless we've multiplied it by some uh, well, it has to be a non-denominate number unless we've multiplied it by some denominate number whose numerical value is one, so it's just a bunch of units out in front. That could be a possibility, but we haven't done that, so we know that shouldn't be happening. Uh, but that's it. That's the expression. And the big thing is if you look at v of t and you take it in the limit as t approaches infinity, what you get, of course, is the limit of mg over b times 1 minus e to the negative b over m times t. So you can actually interpret that as 1 over e to the b over mt. So you can see that the e with bt over m as the exponent is actually in the denominator. And if you allow that exponent to go to infinity, then 1 over the that whole exponent is going to go to 0, and you basically just get mg over b. And that means that v, what we call specifically v terminal, is equal to mg over b. So you can see that we reach a terminal velocity specifically when b times v is equal to mg, and that should make sense because if you look back at the original problem, when this velocity going down gets big enough that it's mg over b, then this v right here becomes mg over b. So the b cancels out with the b down here, and you're just left with negative mg and positive mg. So you have a mg pointing down, and then you have minus mg pointing up, and that gives you a net force of 0, and therefore the terminal velocity is when mg equals bv. Any questions on that? So that was the one part that we definitely got right last time when I did it. I still ain't figured out what I did wrong, but anyways, I fixed it. So hopefully that helps. Anybody have any questions on that or any other stuff from chapter 5?
Is B usually given, or do we have to solve that with an initial condition or something?
Yeah, they would have to give it to you. If you study fluid mechanics a little bit more, you'll get into, I want to say it's Poisson's equation or Pucell's equation, and that actually tells you partly what the B is, but the B actually comes in when you are taking account of something falling. You have to take account of the cross-sectional area. So, for instance, if the thing that was falling was, say, this Rubik's cube's about, 1.5 centimeters plus 1.5 centimeters is three, about 4.5 centimeters by 4.5 centimeters. So that area 4.5 centimeters times 4.5 centimeters is part of that B. Another part of that B is something called the viscosity of the fluid that you're going through, which in the case of air, it has a fairly low viscosity. But you could imagine if you drop something in water, that would have a much higher viscosity than air. But if you did it instead, like in syrup, then it would have even higher viscosity. So that's what that B really depends on. It depends on the cross-sectional area. And what I mean by that is whatever direction you're going, you want to imagine the shadow it would shine down the ground if you were shining, a million lasers straight down above it so that it would make an actual exact replica of the size of the face of the cube that's pointing down. That little area is what we call the cross-sectional area on it. So hopefully that's explanatory. But yeah, they have to give it to you, or in some cases, like I said, they could allow you to calculate it because you might have access to a table of viscosities, for instance, like for motor oil or something like that. They might have given you the dimensions of the object and told you what its orientation was when it fell down, or they could just outright give it to you. Does that make sense?
Yeah, and one more. Why does drag depend on surface area, but friction only depends on mass?
Well, it turns out that if you actually try to calculate what's happening with air resistance or air drag, as we call it, it's literally molecules bouncing off the front face of the thing. So whatever thing is falling, you're not only falling, but that front face has to push sort of the air out of the way. And because that front face is pushing the air out of the way, the size of that front face dictates how much air you got to push out of the way. So there's no way of avoiding having to take into account the cross sectional area. Whereas the regular friction that, sliding on a surface or something like that, it feels like you would expect it to have some dependence on the area of, touching, for instance, but it evidently does not based on our own experiments and stuff like that. And we can sort of make an argument for it. Specifically, the friction force, uh, in some sense, is like at the molecular level or at the fine grain level, there's a little roughness in surfaces. If you go to the actual microscopic, atomic level, you'd see that there's not even a clear indication of where the edge of this tabletop is because there's electrons flying up and out, up and over, individual atoms coming up from time to time, and they're bumping, but they can actually cause molecular forces on one another. And it just turns out that evidently it doesn't depend on that cross sectional area. So a lot of the things that we originally thought might be causing friction based on experiments seem to not be as important as we thought. And it turns out to just depend on the two surfaces and what they're made of, basically. Okay. So I don't know if I gave you a good enough answer, but that's about as good of an answer as I could offer, giving my limited knowledge in that particular field. This, why, when I write the word drag, I really look like a moron. Okay, there, it looks better. Never mind it having the wrong color, but anyways. So let's get started now with the chapter on gravity. So uh, if you read the Principia, I actually have a copy here. Hold on a second. The only reason why I'm even taking the time to show you this is because a lot of people don't understand how big of a volume the Principia is. But this is my personal copy of the Principia. You can see that's a pretty big book. This one actually has the Latin as well as the English in it. But if you flip through it, you'll see it's a lot of words. There's not nearly as many equations as you expected, and there's a lot of geometric drawings. And that's because, in Newton's time, we didn't have access to calculators like we did. So a lot of the work was able to be done more rapidly by using geometry. And of course, Newton happened to be a genius. So if anybody's going to have to solve physics problems by using geometry, I would want someone who's a genius, and specifically a genius at geometry to do it. And Newton certainly fits that bill. So that's one of the things I wanted you to notice. But the other thing was I wanted to tell you that in his Principia, he says that he was sitting in an orchard. His mother owned an apple orchard, and in fact, she sort of pimped him out in some at least disgusting way compared to modern uh, civility and stuff like that. But she did more or less pimp him out because he had an uncle who had taken an interest in him because he was so brilliant, and his uncle was fairly well off, at least in terms of he had a job and could get enough money because he worked for the church. But he would bring him books back and forth from the libraries and things like that. And he found out that Newton was really brilliant at math. And Newton had actually been working through the books as opposed to just reading them. He'd actually been doing proofs and stuff like that at the age of 8 through 12. And he goes to the mother who is really a single mom. Specifically, she was impregnated by Newton's father, and then Newton's father just disappeared. So I don't think Newton ever met him, and she may or may not have even known exactly who the father was. But either way, she's raising a son by herself, and the only income she has is her little apple orchard. So when this gentleman, who's related to her in some way. I would assume it's like her brother, but it could have been the brother of the husband. I'm not, or the brother of the father. I'm not sure. But the main thing is, he told her that he's too brilliant. We need him to go to Cambridge. And she said, "Well, there's no way I could afford that." He said, "No, no, no. I'm willing to pay for him to go to Cambridge." And then she buckles down and says, "Well, actually, I don't think I could make ends meet around here if I didn't have him working for me." So she literally like shook down the uncle for more money, which made less money available for Newton. And in fact, Newton ended up having to work his way through college, where the guy paid the tuition, but you still had room and board. And lo and behold, his job was cleaning the chamber pots for the wealthy kids. So you can imagine he had just a wonderful life where everybody treated him wonderfully nicely, since the upper echelon children would see him early in the morning and late at night to empty out their poop and pee. So, anyways, it was kind of an ugly situation, but Newton had a lot of issues. If you read any history of it, I highly recommend you read a history of Newton and pretty much all these scientists. But they're very interesting characters. He, for instance, wrote over 500,000 words on the Bible. He was reading the Bible in the Greek, the New Testament in Greek, which is what it was originally written in, and he was convinced that there were, critical numbers that were in the Bible that could lead him to like a fountain of youth, or perhaps some answer for the problem of alchemy, which is turning lead into gold, stuff like that. He also wrote a couple 100,000 words on optics and did a lot of experiments with optics as well. Uh, he did have he had several notebooks. People kept books back then as, sort of like diaries or whatever, but the upper echelon scientists and thinkers definitely kept them. Newton, and of course later on you'd hear of John Adams, or Thomas Jefferson, or Francis Bacon, sort of about the same time with Francis Bacon. But either way, you hear these people doing this, and we finally managed to crack the code that was necessary to read Newton's famous notebook of his own personal thoughts and stuff like that. And everybody's like super excited because Newton's this interesting character who, at the ripe old age of 80 something, I think he lived to be like over 80, but he was like in his 70s or something. And he bragged that he was a virgin. And everybody wanted to know, what kind of secrets could Newton be hiding. And finally, we cracked the code and figured out how to decode his personal book. And you read through it, and it's like, 1,000 pages. Well, I'm exaggerating. It's a bunch of pages where it just says, "Forgive me, Lord, for today was the Lord's day, and I worked," or "Forgive me, Lord, I got angry at such and such." But really, really a pious, dutiful character who's main obsession was doing right by God and stuff like that. And that's kind of neat. But then all of a sudden you run into this one page and it says, "Forgive me, Lord, for today I wish the death of 50 people." And like, now that's the Newton we expected to see. So I do recommend you reading that. But I'm going to go on now and tell you that, like I said, in his Principia, he said he was sitting in the apple orchard and he looked up at an apple in the tree, and then in the distance he saw the moon. And at that point, he realized that the moon and the apple were not so different. In fact, the apple will eventually get so juicy and succulent that it'll be so heavy that the stem can't hold it anymore to the limb, and it'll fall to the ground. And he, had been studying the laws of nature. And of course, Galileo, who was literally died 100 years to the day before Newton was born. Actually, no, I think Newton was born the same day that Galileo died. It was either that or like exactly 100 years. I can't remember. Feel free to check me out on that one. But it's really an interesting thing. And you can imagine Newton definitely paid attention to that, as did Stephen Hawking when he basically was born on the same day that Newton died, but obviously many years different. But either way, he actually had studied Galileo, and he knew Galileo's law of inertia, which basically said it's as if an object has a certain inertia that makes it reluctant to speed up or slow down or change direction. So he had learned that. So he's thinking, here's the moon flying by the Earth. In principle, the moon would tend to keep going straight at whatever speed it's going and not be deflected by the Earth at all. But what if that force that happens to be pulling that apple from the tree stem that broke down to the ground? What if that force is the same force that pulls the moon off of its straight line track so that it falls just enough that it never gets any further away from the center of the Earth? Well, that was a pretty good hunch. And in fact, he had been, as I told you, he studied optics, and he had learned that light, the intensity of it, in other words, how bright it was, fell off like 1/the distance squared, which means if you're like, and remember, in this time period, they didn't have electricity, so he would have used like a little flash, not a flashlight, a little candle or something like that. So you can imagine a small flame, and then imagine how bright the light would be, let's say 1 meter away from the small flame. Well, if you went instead and compared that brightness at 1 meter to a distance of 2 meters, the 1 over r squared law would say that distance 2 meters away would cause the brightness of the candle to be 1/4 as big as the brightness at 1 meter. And if you went to 3 meters away, it'd be 1/9 as high an intensity as the 1 meter one. And if you went 4 meters away, it'd be 1/16. 5 meters would be 25, so on and so forth. So his idea was, I wonder if whatever this force is falls off like 1 over r squared. And he just said, well, if it did, then I know that the apple, which is essentially sitting on the surface of the earth, remember, if you consider, for instance, the highest point on planet Earth, which is Mount Everest, and then the lowest point on the surface of the Earth, which is at the bottom of the Marianas Trench, uh, that's a pretty huge distance. But it turns out, even with that maximum high of Mount Everest and that maximum low of the Marianas Trench, the Earth is still more of a sphere than a basketball is because of its pimples and grooves. So the basketball is literally less perfect of a sphere than the Earth is, even with those monstrously large mountains and stuff like that. So his idea was that clearly, since the tree is so small compared to the radius of the Earth, then the apple is literally one Earth radius from the center. And he knew that the acceleration that the apple gets when falling from a tree is what we now call 9.80 meters per second every second. And he said, well, he also knew that the moon was 60 Earth radii from the center of the Earth. So if it's at 9.8 at 1 Earth radii, he'd expect it to be 1 over 60 squared times 9.8 for 1 Earth radii, I mean, for 60 Earth radii. And if you actually take that quantity and you say g over 60 squared is equal to 9.80 meters per second every second divided by 3600, you get 0.00272 meters per second per second. So that was kind of a big deal. Now all they had to do was see, well, what exactly would the acceleration of the moon be given its parameters? Well, its parameters are this. The acceleration is the centripetal acceleration, which we learned about in the previous chapter, which is just v squared over r, where r would be the distance from the center of the Earth, which is the center of the revolutions, to the center of the moon. And of course, v, since it's going, we're going to assume it's in a circle. It turns out it's really close to a circle. It's not a circle, but it's really close. And in fact, all the planets are really close to circles. The planet that's the worst was demoted to not be a planet. That was Pluto's. But I swear, if you drew a perfect circle, let's say 4 foot in diameter, and then you drew a perfect replica of Pluto's orbit such that it was 4 foot in diameter at the biggest point, you couldn't look at those two next to each other and figure out which one's the circle and which one's the orbit of Pluto unless you were able to do quite a bit of measurements before you could tell it. Okay, so that gives you an idea of how circular these orbits are, even though you know for a fact that Kepler told us the orbits were elliptical. So we're going to treat it like a circle, and an object going in a circle has to complete a distance around the circle. And what's that called, the distance around a circle? It's called the circumference, right? Uh, so the velocity would be distance divided by time. It turns out, as we learned last semester or last chapter as well, that when you go in a circular orbit, you generally have a constant speed. So all I need to do is figure out the distance and divide it by the time taken. Well, when you're talking about the time taken to complete an orbit or something that repeats itself, that time is called a period. So we're going to take the circumference and divide it by the period of the orbit. Well, the circumference is 2 pi times the radius of the orbit, and the period is 27.3 days. The radius of the orbit, r, is about 384,000 kilometers. So we're going to check what that calculation is, and I'm going to double check, make sure my number's right about the 384,000. But just double checking here. Yep, yep, yep. The moon is 384,000 kilometers from the Earth. Yes. He actually used the 60 Earth radii, so I could have used the Earth radius and then multiplied it by 60, but this is good enough. So what I get now is that the velocity will be 2 times pi times 3.84. Now, right here, you see if you wanted to convert this 3.84 or this 384,000 kilometers to scientific notation, you'd call it 3.84 times 10 to the fifth. But we need it in meters, so it's going to be 3.84 times 10 to the eighth meters. So that's our circumference, 2 pi times that number. And then we also have to have the period in seconds. So I take the 27.3 days and I multiply that by 1 day is equal to 24 hours. And then I take the idea of 1 hour and realize that that is in fact 3,600 seconds. So you can now see that the hour cancels out with the hour and the day cancels out with the day. So we're finally left with meters in the top and seconds in the bottom. When I do this calculation, I hope you're doing it too because it's kind of very big deal, kind of exciting. 2 times 3.14159 times 3.84 times 10 to the eighth. All of that divided by 27.3 times 24 times 3,600. And notice I did say I put parentheses around that denominator. So now I'm closing off the parentheses and the answer I got is 1,000, oops, is 1,022.903 meters per second, which is way more sig figs than necessary. Now I have the velocity. I can calculate the centripetal acceleration. The centripetal acceleration is supposed to be the velocity squared divided by the radius. So I'm going to take the 1022.903, which should really only have 3 sig figs, and that's meters per second. I'm going to square it, and I'm going to divide it by 3.84 times 10 to the eighth meters, and that's going to give me, let's first off square that quantity, and then I'm going to divide that by 3.84 times 10 to the eighth, and lo and behold, that gives me 0.00272. And there's some more digits, but we only had 3 sig figs, so the rest don't really matter. But the next one, for instance, is 4. And that result is meters per second every second. At this point, Newton doing this calculation he realized he's the only person on planet Earth that knows exactly why Mercury orbits the sun, Venus orbits the sun, the Earth orbits the sun, the moon orbits the Earth, the Galilean moons orbit Jupiter, and so on and so forth. So that's pretty neat, right? He just figured out that the force F is proportional to 1 over the square of the distance between them. And we ultimately get Newton's law of gravity is this. He said the force is directly proportional to the product of the masses. So if you imagine two particles of mass m1 and m2, and I'm saying particles because you can think of them as so small that they only take up a single point in space, and then there's no ambiguity about how far apart they are. They're from the point to the other point, right? So it's directly proportional to the product of the masses, m1 times m2, and it's inversely proportional to the square of the distance between them, which we call r. And here's the other part. He said that the force acts along the line connecting the two point charges, the two particles. So the force has to be along the line connecting the two particles. If they happen to not be particles, but they're spherically symmetric, it turns out you can just go from the center of one sphere of mass to the center of the other sphere of mass, and that would give you the distance, and it would also give you the line along which the force is parallel. Okay, so that's a really big deal. And you know from high school algebra one that whenever you have an expression like F is directly proportional to the product of the masses, all you have to do to make that an equation instead of a directly proportional statement is you have to add a constant. So we ended up adding a constant that we call capital G. So this is Newton's law of gravity, and we call it Newton's universal law of gravitation. And there's many reasons why. So let me explain a little bit. When we say universal law of gravitation, what we mean is at least twofold. One, we find that any two objects that have mass, no matter what, according to this argument, they must attract each other with a gravitational force. And that force is only attractive as far as we can tell. We've never ever found a particle that has a repulsive force, which, is sort of the opposite of what we discovered when we're talking about positive and negative charges, or when we're talking about north and south poles of magnets. North pole and a north pole avoid each other like the plague. A south pole and a south pole does the same thing. Two positive charges do the same thing. Two negative charges do the same thing. We've never found anything like that with gravity. So as far as we can tell, it's always going to be a attractive force, and it's directly proportional to the product of the masses and inversely proportional to the square of the distance between them. And the G turns out to be G is equal to 6.67 times 10 to the negative 11th, and that's going to be Newton meters squared per kilogram squared. I think it's 6.674 if I want an extra sig fig, for instance. But we're pretty much just going to use probably 6.67. Three sig figs is usually enough. Anybody have any questions on that part? Okay. I'm checking something right quick just to make sure. I thought it was going to be a real easy thing for me to double check my value of G, but it's taken me a lot longer than I expected. So I apologize for that. Here it is, my value of G. Whoa, 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 went a little fast there. Okay, so I'm clicking on the thing and no, it's 6.673 times 10 to the negative 11th. My apologies. Again, not necessary that you know that many, but sometimes you do need it for a calculation. So now you've got an extra digit. And in fact, if you look at the bottom of your practice tests and the bottom of your online tests and the bottom of your face-to-face test, you'll see that there are copies from the inside and front and rear covers of the hard copy of this textbook, and it has G to like 4 or 5 different decimal places. It might even have like 8 decimal places. So That's that. That's the way the law of gravity works. Another reason that it's universal is, like I said, every mass, every one mass is attracted to every other mass, period. So it is universal. It means anything that has mass will universally be attracted to anything else that has mass. But it's also universal in that there's no distance r you can put in Newton's law of gravity that gives you a force of zero. So this force literally reaches infinitely far away. It doesn't reach zero until you literally get infinitely far away from the other mass. So that's a couple reasons why it's called the universal law of gravitation. And now we can show you how to use it. So for instance, what you might want to do is estimate. So this will be example two. Let's say estimate the gravitational force of attraction between two people. Okay. So solution. In this case, we're just going to imagine two normal sized humans. Let's say M1 is 80 kilograms, and let's say M2 is 100 kilograms. So, somebody that's a little fat like me can be counted, and then somebody that's more normal size, like 80 kilograms, they can be counted. And let's imagine that the distance between them is on the order of 3 feet, so like roughly a meter. So we're going to say R is equal to 1.0 meter. This should give us a rough estimate about how large this force is. So the force, according to Newton's law of gravity, would be 6.673 times 10 to the negative 11th newtons meters squared per kilogram squared times 80 kilograms times 100 kilograms. Notice how the kilograms are canceling out with the kilograms there, leaving Newton meter squared. Now we're going to take that and divide it by 1.0 meters squared. And now you can see that this meter is going to cancel out with these meters squared there. So you do know that the force comes out to be in units of newtons. So I'm going to say 6.673 uh, times 10 to the negative 11 times 80 times 100, and then I'm going to say divide by 1 squared, which luckily we don't even have to do. And lo and behold, I get a force of 0.000. There's three zeros there. And then there's another three zeros. And then there is a digit of 5 newtons. And we pretty much were estimating to the nearest sig fig, to 1 sig fig. So we could call this 5.0 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 newtons. So basically a half a million. Yeah, that's right. A half a million Newton, a half of a millionth of a Newton. Sorry about that. So that's really, really small, especially considering the Newton's only less than a quarter of a pound. So, yeah, the gravitational force is notoriously weak, and you can see that's partly because this G, which was 6.673 times 10 to the negative 11th Newton meter squared per kilogram squared, well, that equals 0.00000000667. So that's how small that number is. We'll later learn about Coulomb's law, and Coulomb's law F sub c looks identical to Newton's law of gravity. One thing we can use is a k for the constant, and instead of Q1 and Q2, or excuse me, instead of M1 and M2, we use Q1 and Q2 because Q is the symbol we use for charge. But lo and behold, it still has the R squared. So you can see instead of multiplying two masses, you're going to multiply two charges. And the reason why I'm showing you this is because this particular value of K is 8.988 times 10 to the ninth Newton meters squared per coulomb squared. Notice kilograms was in the bottom of the G, but in this case it's coulombs because that's the relevant thing. So you can see this thing's on the order of a billion, whereas the gravitational constant is on the order of a decimal point followed by 10 zeros followed by a 667. So you can tell already that yes, gravity does reach infinitely far, and therefore it's in some sense, the master of the universe. But guess what? Coulomb's law also reaches all the way across the universe. And it should be a lot bigger, but it doesn't affect life day in and day out quite as bad, or at least it doesn't affect planets and stars and stuff as bad as the gravitational force does. Can anybody think why the Coulomb force doesn't? It's okay. I was hoping you might have heard it before from, say, your chemistry class or something like that, but it turns out matter is, when we find it, it's almost always neutral. In other words, complete atoms normally have the same number of electrons as atoms, or excuse me, as protons, so that the net charge of the atoms are zero. And because of that, the forces, which could be really, really large, just don't appear that often because things are generally not charged. All right. Now, I think that's enough of the background stuff, but we could use, for instance, an idea of roughly how big of the force of attraction is between, let's say, the moon and the Earth. So let's try that as our next example. This will be example three. Estimate the force of attraction between the Earth and the moon. Okay, so solution. Now we need some information. Obviously, Newton's law of gravity says F is equal to G m1 m2 over r squared. We do know that the distance between the two planets, are between the Earth and the Moon. Obviously, the Moon's not a planet. We know that distance is 3.84 times 10 to the eighth meters because we just finished doing that a couple minutes ago. We don't necessarily know the mass of the Earth, but the cool thing is your book has on the inside cover, or in various tables in the online homework system. It has this kind of information for you, but we also have the Google machine in front of us, so I can just type in mass of Earth, and it tells me it's 5.972. So I'm going to say M, and this is the astronomical symbol we use for the Earth, is basically a circle with a plus sign in the middle of it, and it's 5.972 times 10 to the 24th kilograms. And we also need the mass of the moon, so I'm going to just erase the word Earth and write in moon. And we found that that one is the mass of the moon I don't know of the cool symbol that astronomers and cosmologists use for the moon, or if they even have one. But in this case, I'm going to say the mass of the moon is about 7.347, I know 7.348 times 10 to the 22nd kilograms. So we have what we need now to do that calculation. So we're going to calculate that force, and it turns out that force is going to be 6.673 times 10 to the negative 11th Newton meter squared per kilogram squared. Uh, if you can't work these units out in your head, uh, then it's probably best to go ahead and write them out, at least while you're doing your homework, so you can get used to it. In a test, you might not want to take the time to write all the units out, but you definitely need to be checking them because that's the difference often between 100 and a 82. So it just often can come up to just careless unit mistakes. So that's why I'm showing you all this. The mass of the Earth, it doesn't matter which order, but the mass of the Earth is going to be 5.972 times 10 to the 24 kilograms. The mass of the moon is going to be 7.348 times 10 to the 22 kilograms. And the distance between them is going to be 3.84 times 10 to the 8th meters. And that's got to be squared. So now I can do 6.673 times 10 to the negative 11 times 5.972 times 10 to the 24th times 7.348 times 10 to the 22. Now I'm going to take that and divide it by 3.84 times 10 to the 8th, and I'm going to square that. And that gives me a force equal to 1.99. That's good enough. That's the 3 sig fig. So 1.99 times 10 to the 20th newtons. So that just gives us a ballpark figure of, how big is the force of gravity that is pulling on the moon. So, it might be interesting to know, how strong of a force does it have to be for us to move that moon, which we know is on the order of about 1/100th the mass of the Earth, but still huge, huge, 10 to the 22. By the way, the mass of the sun, I think that's on the order of 10 to the 31st, and I think it's 1.99 times 10 to the 31st kilograms. So that gives you an idea how much bigger the Earth is than the other planets. For instance, if you consider the mass of our solar system in total, it turns out that the sun makes up well over 99.99%. So that's taken into account not only all the planets, but all the gas and dust, as well as all the asteroids in the asteroid belts, as our asteroid belt, as well as all the uh, parts of the disk particles that are on Jupiter, Saturn, Uranus, and Neptune, the comets in the Oort cloud, and the comets and other asteroids and stuff like that. That's actually in what we call the Kuiper belt as well. All of that stuff added up makes up well under 0.01% uh, compared to the whole. Okay. The sun, on the other hand, makes up about 99.99%. Any questions on that one? Okay, so one of the big things you got to know how to do is obviously it's something about vectors because you've seen, for instance, in chapters 3, 4, and 5 now that vectors are kind of important. So one of the things you have to be able to do is take a formula like this one, F equals G M1 M2 over R squared, and that's a formula that gives us a magnitude. But it came with that sentence. Remember, I told you the force is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. And this part of the sentence is what I'm talking about, acts along the line connecting the two particles together. Okay, so that gives us enough to make not only the magnitude but the direction because we know all the forces are attractive. So you always draw it from one object towards the other object along that line. So that's something we got to be able to do. And other than that, we also need to just be careful and make sure we can do some of the more simple orbital type calculations. So let's look at another example. This was example 3, so I'm going to do example 4 now. Feel free to ask me any questions if you have any. Uh, what we're wanting to do is basically calculate something related to an object in orbit. So, what I'll say is what. Whoa, Nelly. Hold on a second. What is the force? What is the gravitational force? Force of attraction between a 2000, which I'm going to assume this to be 4 sig figs, kilogram space station orbiting at 2 times the radius of the Earth, where the radius of the Earth, I'll use this symbol again, the radius of the Earth is 6,380 kilometers. I'm going to treat that as if it's 4 sig figs as well. And the Earth. Okay. What is the space station's orbital speed? So we're saying this orbital is obviously a circle because we said it was a certain fixed distance away from the center of the Earth, namely 2 Earth radii. We have the information that we need. For instance, the mass of the Earth. Is that what I used earlier? The mass of, yeah, 5 point. We'll access right it here. I'm going to do solution, and we have the mass of the Earth, which is equal to 5.972 times 10 to the 24th kilograms. We have the mass of the spacecraft, which is equal to 2000 point kilograms. We have the distance between them is 2, or I'll just write it like this. I'll say R is equal to 2 times 6,380 kilometers, which obviously we have to put that in meters. And that should be it for this part. We also are going to need for part B. So part A, what we wanted to find was F equals question mark, but part B, we wanted to know V of the spacecraft is equal to question mark. So I'm going to go ahead and write first off for part A, 6.673 times 10 to the negative 11th. I've got enough practice with the units. I'm not going to write them this time. 5.972 times 10 to the 24th kilograms for the Earth, and then times 2000 for the spacecraft. And then I'm going to divide all that by uh, 2 times 6,380 is equal to 12,760. So I'm going to say 12,760 kilometers times 1 kilometer is equal to 1,000 meters. And then we got to square that. So if I want to calculate this force, I'm going to do 6.673 times 10 to the negative 11 times 5.972 times 10 to the 24 times 2,000. And now I'm going to say divided by 12760 times 10 to the third, and I'm just going to square that. And that gives me 4,895 newtons. So even with that big of a planet, that close, we're only getting about 4,900 newtons. To give you some perspective, for instance, the weight of the spacecraft, which would equal the mass of the spacecraft times g, would be 2,000 kilograms times 9.80 meters per second every second. And when you multiply those, you get 19,600. And that's uh, greater than twice the force of gravity between the moon and this, or excuse me, the Earth and the space station. Okay. So yeah, that's a big force, 4,900 newtons, but it's also a very small force when you're thinking that one of the things doing it is 10 to the 24th kilograms, and the other thing actually weighs more than twice as much as that force. So that's kind of a big deal. But anybody have any questions on that one? Now, you could also have done this a lot smarter and easier way. We could use the same argument, for instance, that Newton used. So here I'm going to do that this way. Another way. Newton argued that A, due to gravity, was 9.80 meters per second at r equals the radius of the Earth, and A, due to gravity, was equal to 0.00272 meters per second, which also happened to equal 9.80 meters per second divided by 60 squared at 60 Earth radii. So we expect the weight, or we expect A, due to gravity at 2 Earth radii, to be 9.80 meters per second divided by not 2, but 2 squared. Okay, just like it wasn't 60 that we divided by 60 squared. And if we do that, we do 9.8 divided by 4, which is equal to 2.45 meters per second every second. Therefore, the weight at R, or excuse me, I should say the weight at 2 times the Earth radius should be equal to m times g at 2 Earth radii. So that would be 2000 kilograms times 2.45 meters per second. So there its weight would be 2000 times 2.45, which gives me 4,900 newtons. So that's kind of neat that it turns out to be so close to exactly the weight at that particular location. Anybody have any questions on that? All right. I think I'm going to go into, before I do more calculational stuff, I'm going to go into Kepler's laws because we only got like 5 minutes left. So we're going to say Kepler's laws. So if you learned anything about this before, you'd know that there were several scientists involved over the history of the Earth with regards to models of the universe. For instance, Eratosthenes was the first person to actually do a calculation of the radius of the Earth. Aristarchus, around the same period, plus or minus 100 years or so, was the person to conjure up the idea of an atom, and from that, we were also able to do things like think about uh, how to how were things in this in outer space oriented and placed and stuff like that. What were those things? We had ultimately Ptolemy and Aristotle put together a fundamental model, and the idea was, even the ancient Greeks had thought about this. The ancient Greeks thought there's a good chance that maybe the sun is the center of everything, and they say the center of the universe because they didn't realize, and in fact we didn't either till around 1905 to 1915. We didn't realize that there were other galaxies in the universe. We thought it was pretty much our solar system, and then the on the order of 10,000 stars that we can see in the night sky. We expected that maybe there'd be more stars further out, of course, but that's all we could see. But we didn't necessarily know there were going to be other islands of stars like our galaxy. And it wasn't until Hubble used a 100-inch telescope that he discovered that one of the nebulas, which is a little cloudy area in the sky called the Andromeda Nebula, turned out to be actually an island of stars that might, in fact, be even bigger than our galaxy. Our galaxy, I think, is our latest figures is probably on the order of 400 billion stars, or 400 billion solar masses of stars, and the Andromeda galaxy might be twice as big as that, right? But when he looked at it with a telescope, he could see that it's individual stars orbiting around a center, and that was very far away. So our universe came really bigger at that time. But at the time, they said, well, this is the universe, and they argued if the sun was the center, then when the Earth was over here, it could look at a really distant star and get a some image of what the stars look like. But then when it went over here, the nearest star would actually show some movement. So, for instance, when I'll draw it like this, we'll say this is the sun, we'll say this is the earth, and we'll say this is the earth as well. This is, say, the earth in December, and this would be the earth in, say, June. And in June, the stars might look something like this. Uh, but when we come over to here, what we might find is that the stars look, actually, I need to do a different color so it looks somewhat correct. What the stars might look like would be something like this, but lo and behold, here's the weird part. That one's that. Let's say this guy moved all the way over to here. It used to be over here, but now it's not. And what we've seen is that this star moved from here all the way over to here. That's because that particular star was was closer to us than the other ones. So, for instance, if you put your finger in front of your eyes like this and you close your left eye, what you'll see, or what I see right now, is my finger looks dead center in the middle of the screen. Now, if I close my right eye and open my left eye, now it looks over here on the right side of the window. That's because this finger was closer to me than those distant things. So it moved back and forth. That's called parallax. So the ancient Greeks imagined that the sun could possibly be the center, but they knew they'd expect to see parallax. And they tried to see parallax like that. They tried to see stars moving back and forth between images that they remembered from December versus images that they remembered or drew from June. And when you do something like that, were not able to detect any motion of the stars. So that led them to one of two conclusions: either the universe is way bigger than they thought it was, or the Earth is the center as opposed to the sun. They just could not imagine a universe that big, so they came up with the Earth being the center. And they made a model with that, and then they had to account for planets going backwards sometimes in their orbits. And the way they did that is they imagined that there was the sun or the earth at the center, and then there was giant crystalline spheres. Embedded in each one of those crystalline spheres would be another holy body, like the planet Mercury would be in one, and then the planet Venus would be in one, and then the moon would be in one that's even closer to the Earth than Mercury or Venus, and then the sun would be another one, and then Mars would be another one, and then Jupiter, and then Saturn. But that wasn't good enough. They then had to put epicycles on those circles. Those circles were called differents, and then the epicycle was a little circle on the end, and that could be adjusted so that the rate at which the epicycle rotated around the different and the rate at which the planet rotated around the epicycle and the radiuses of both of those could be altered in their model, and they could get it to fit many, many years of data. And they had literally hundreds of years of data from ancient Greece. And they put together this this geocentric model that was called the Ptolemaic or the Aristotelian model forever. Other people saw problems with that. Tycho Brahe was one of them. Galileo was the big one that came along. Copernicus didn't even know that necessarily. He just was sort of not part of what I'd call the scientific revolution because he thought we should switch to the geocentric just because we had lost our way from what Aristotle taught us. But what we came up with was Kepler's three laws. I'm just going to tell them to you and then let you go. The first law is the planets travel in elliptical orbits, not circular, with the sun at one focal point. We'll explain that again later. The planets sweep out equal areas in equal times. That's Kepler's second law. Uh, that turns out to be a ramification of conservation of angular momentum. And then the third law was that the square of the periods of the planets is proportional to the cube of the semi-major axis of the planets. And the semi-major axis is something like the radius. Okay. So those are Kepler's three laws. I'll show you more about them and we'll do more calculations next time. But that's good enough. If you haven't already chatted me your first and last name, make sure you do. So I have it for roll. You guys are free to go. Do not forget to do your do your face-to-face test that's supposed to be proctored. I sent out an email about that yesterday. You also had one that was due. I think it was due last night, if I remember correctly. So hopefully y'all got that done. But anyways, have a good weekend. Stay safe, and let me know if I can do anything for you. Remember, you have a deadline. Ideally, you should do it before then, but you can do it as late as Monday, and that's your your face-to-face test. Okay. Have a good one, people. Thank you. I'm going to stay till the last person leaves in case anybody has any questions. Zach, you still there? You have any questions? I suspect Zach has left the building. Okay, just to rehash in case anybody didn't hear them, Kepler's first law, the planets follow elliptical orbits with the sun at one focal point. That's Kepler's first law of motion. of planetary motion. Kepler's second law of planetary motion, the planets sweep out equal areas in equal time. That's the second law of Kepler's planetary motion. And then Kepler's third law of planetary motion, the square of the periods of the planets is proportional to the cube of the semi-major axis of the planets. And that's it. So I hope you enjoyed it. Keep an eye out for other videos I might make later. Have a good day. Bye bye. Bye bye.